Hello everybody, Mr. Ace here. Today we're going to be continuing section 12.3 talking about solids. We're going to start off by talking about the characteristics and densities of solids. So the first thing I want to say is about density and about water, because one of our most common experiences dealing with liquids and solids is the fact that ice floats on water. But in general, most solids are more dense than their liquids. However, water is the opposite. The liquid water is more dense than the solid, and thus ice floats on water. That is not common. It seems common to us because one of our most common experiences with densities and floating and liquids is ice and water. However, most solids are more dense than their liquids. So we've been talking about the kinetic molecular theory. And it says that all particles are moving. We talked about how in gases, the particles have so little attractive forces between them that the particles just jump around. They just bounce around all the time. They're constantly moving. They're not really sticking together. In a liquid, there's enough attractive force that the liquid will stay bound together. It's not going to all of a sudden jump up. It's going to stay all bound together. It can flow. It's loose enough that it can flow. But in a solid, all the kinetic energy pretty much has to be vibration in place. In a solid, all the particles are connected into fixed positions typically, and they can't move from those positions. So if we talk about some of the properties, we've talked about how these respond to the concepts of volume, shape, and compressibility. Gas will expand to fit whatever its container it is in. So the volume of the same amount of gas can change. But liquids and solids have fixed volumes. Solids have a fixed shape, as opposed to gases and liquids. Those are called fluids because they do not have a fixed shape. But solids do have a fixed shape. And compressibility. Gases are compressible, liquids and solids not so much. So today we're primarily going to be talking about different types of solids, starting with the largest category, which is crystalline solids. So what a crystalline solid is a solid whose particles are in orderly geometric patterns. Now, the smallest unit of those is called a unit cell. So this is the smallest arrangement of that shape. So we looked at some of these shapes back when we talked about ionic crystalline solids. So we have cubic, which is exactly a cube like you think it would be. It forms when now there's different ways to form a cubic, but basically the particles arrange themselves evenly spaced in a cube as you think that a cubic thing might. And remember, there's one back here. And they arrange like that. Tetragonal is kind of like these other two, tetragonal and orthorhombic. I have a hard time saying that. Orthorhombic. All have 90-degree angles, if you know. But basically how different they are changes. So, for instance, two of the sides are square in a tetragonal, but the third side, the height, is not. Whereas all three can be different in orthorhombic. So those are three different ones, all kind of based off 90-degree angles. Now there's other ones that don't have 90-degree angles. We have triclinic down here, which is where we stop having 90-degree angles. We have hexagonal. We have rhombohedral and monoclinic. Now I don't expect you to know that all these specifically, but it's important to know they can form a lot of different shapes, and how they form these different shapes is based on how their particles arrange. So types of crystalline solids. So there's a lot of different ways crystalline solids can be formed. The first type is a molecular solid. And as the name implies, molecular solids are built out of molecules. Remember, molecules are covalently bonded. So that's where they're sharing electrons. Now, because they're covalently bonded, this typically means they have low melting and boiling points. In fact, most covalent substances we know are not solid. Really large, molar mass-wise, particles can be solid, like sugar. But things like ice are only solid when we freeze them. And so oftentimes they have to be cooled down to be made solid. So important things to note, they're held together by a combination of dispersion, dipole-dipole, and hydrogen bonds. They tend to be soft, and they tend to be poor conductors. Now, ionic solids are held together by ionic bonding. That means they typically have high boiling points and high melting points, because ionic bonding is a lot stronger than covalent bonding. And these can be decent conductors when dissolved into water, but otherwise typically no. So whether or not they're considered electrolytes, they don't conduct normally, but if you dissolve them, they will. They are hard and brittle. We talked about it before. If you smash an ionic solid, it will shatter. It has very brittle properties, meaning they'll shatter very easily. Covalent network solids are, as their name implies, covalently bonded. They're usually singular elements that are nonmetals. So examples of these would include carbon, when carbon's by itself, silicon. Now, interesting thing about covalent network bonding is it really opens the door for what are called allotropes. Allotropes are where you have the same material but different structures. So carbon comes in many different forms. It comes in graphite, diamond, and if you get both of those are naturally occurring. You can actually make something called C60, which is where you take 60 atoms to make one covalent network, and that's called a buckyball. They use similar technology to make something called Bucky tubes, which are fully carbon tubes that are incredibly strong. So there's a lot of different, and those are called allotropes of the material. Allotrope means that it's just a different combination and shape based on the geometry. So metallic solids, we know that they are metallically bonded, which means they are cations attracted to the ion C, or the electron C. That means that they have relatively low melting points but high boiling points. They are good conductors of electricity. And they tend to be malleable and ductile, which means that you can reform them fairly easily. So all these form crystalline structures, and they all have different properties. So the different properties of different solids kind of are based on what type is it. Molecular solids tend to be easy to melt. They are poor conductors. They're soft. Ionic solids are hard and brittle. Covalent network solids can take on many different forms. They are covalently bonded, but because they're single elements, they can be hard to melt or boil. Metallic's easy to melt, but hard to boil. They're good conductors and malleable. So all the different properties that you can think of a solid, you can kind of go, which one of these categories does it fall in? Most substances will fall into it. Now, there's one class of substance that don't fall into these categories. Non-crystalline solids, which are called amorphous solids. An amorphous solid is a solid without a regular shape. So common examples of these include glass, rubber, and some plastics. Now, if we look at this diagram here, a crystalline solid has this regular pattern to it. Notice one purple, every one of them surrounded by four greens, and so on. But in this one, they're not necessarily connected in the same way, and they're definitely not in a regular pattern. This one purple is connected to 5 greens, whereas this one's connected to 3, but it's on the edge. This one's connected to 4. This one's only connected to 3, and so on. So it's a very strange combination, and it doesn't create a regular repeated pattern, and that's why we call them an amorphous solid. So before we end, real quick recap. In terms of solids, we have our crystalline solids, which can be divided into molecular, ionic, covalent network, and metallic. We've talked about all those before except for covalent network. And amorphous solids, which do not have a regular shape to them. All right, that covers our discussion of solids. See you next time.